This video is going to take a look at how we can make a confidence interval for a mean when we don't know the standard deviation of the population. But before we get into that, I want to talk about what's called the student's T-distribution. This is another probability distribution similar to the normal distribution in that it is symmetric about the mean of 0. But its exact shape depends on this thing called the degrees of freedom. When we're talking about estimating the mu, or the mean for the population, the degrees of freedom will always be one less than the sample size. The shape of the student's T's distribution is also bell-shaped like the normal, but it has thicker tails than the standard normal distribution. However, as those degrees of freedoms increase, the shape becomes more and more like the standard normal distribution. Here's what I mean for that. This picture shows first in red what the normal distribution looks like, the one we're used to working with. And this very first curve in the light blue represents the T-distribution with a sample size of 2. Notice it's shorter and the tail is fatter. The next one in shows a larger sample size of 3, then a sample size of 6, and if the sample size gets up to 30, notice at a sample size of 30, that black line almost looks identical to the red line. So the T-distribution looks more and more like the normal as the sample size gets bigger and bigger. You can use a table for the T-distribution, which your text talks about, but I want to use Excel to find T values. And I'm going to show you how that works. We have a command in Excel called T.inverse.2t. We tell it the area and the tails and the degrees of freedom. When we're making a confidence interval, we know the area and the tails is 1 minus the confidence level. Here I'm being asked to look at a sample size of 15 with a confidence interval of 90%. Again, the confidence is that stuff in the middle, so in the tails we've got 100% minus 90%, which is 10%, or 0.1. Therefore, my t value that corresponds with this, we can say equals t.inv.2t, open a parentheses. The probability we want in the two tails is 0.1, and the degrees of freedom we have is 1 less than the sample size. Here the sample size was 15. We want degrees of freedom to be 14. That t value is 1.76. Now that we've talked about the T-distribution, we're ready to find the confidence interval when sigma, the population standard deviation, is unknown. The problem we address with this is that we can only use the z-value, like we did in the previous video, if sigma, the population standard deviation, is known. If we only have s, the sample standard deviation, not sigma, the population standard deviation, we must use the T-distribution to make our confidence interval. The process is almost identical. The only difference is we're going to use a critical t value, and then we'll use s to estimate the standard deviation. Let's take a look at an example. An archaeologist has discovered 7 fossil skeletons from an unknown species of miniature horses. That's my sample size, 7. The 7 fossils have a mean shoulder height of 46.14. So that's our x bar from our sample, and a standard deviation of 1.19. Notice that's only s because it's not the population, it's just the sample. We're going to make a 99% confidence interval for the true mean shoulder height of the entire population of horses. As we did before, we can draw a little picture where we want 99% in the center. Alpha, the tails, is 1 minus 0.99, or 0.01 in the tail. So to find those t critical values, we can go to Excel. Now we want a confidence level equal to 99%, and the sample size we said was 7. So in the tails, we just said was 0.01, so our t value is equal to t.inverse.2tails, the probability of 0.01, comma, the degrees of freedom, which is 1 less than the sample size. 7 horses, degrees of freedom is 6. Our t-value is 3.71. So our t-value is 3.71. Now we can find our error, which is that t-critical value times the standard deviation divided by the square root of the sample size. We just found out the t-critical value is 3.71 times the standard deviation of 1.19 divided by the square root of the sample size, which is 7. When we do that on our calculator, we'll get 1.67 for our error, and then we are ready to make our confidence interval. Our confidence interval is our mean minus the error and the mean plus the error. So when we have a mean of 46.14, subtracting the error of 1.67 gives us a low value of 44.47, comma, when we add 46.14 to the 1.67, we find a high value of 47.81. And so we can say we are 99% confident the true mean shoulder height of these miniature horses is between 44.47 and 47.81 centimeters. So you'll notice this process is very similar to when sigma was known. The main difference is we use S to estimate sigma from the sample, and we use the t-distribution instead of the z-distribution when we don't know the population standard deviation.